Okay, thank you very much for the introduction. Good morning, everyone. I'm Leonardo-A from Università, Politecnica delle Marche, Italy, and I'm going to present the paper entitled A First Evaluation of the Seamless Markerless Augmented Reality Registration System Supporting Facility Management. As mentioned by the title, we are proposing and assessing the accuracy of a seamless markerless registration system for augmented reality, and we are considering for this study the facility management domain because of the huge cost related to operation management activities. In fact, according to recent statistics, only the operation and maintenance phase of facility management accounts for around 50–70% of the total annual facility operating cost, between 60 and 85% of the entire cost of a building, and around 50% of the operation and maintenance time is required for locating elements to be maintained in the space to be focused on. So there is the need to improve the facility management efficiency, and augmented reality can provide a relevant contribution to this activity. For example, AR can support the localization of elements to be maintained in both indoor and outdoor environments, provide real-time instructions to operators in the field, and so on. But to make AR fully applicable, some challenges must be addressed, and in particular, spatial registration, that is responsible for calculating the user position and orientation in order to overlap virtual and real worlds. To this regard, first of all, we have summarized existing localization technologies into this quite big taxonomy. Marker-based method register virtual models using some kind of physical or hyperlink markers. This solution can be potentially applied in mixed environment, but they generally require a preliminary survey, a manual setup, and markers often generate aesthetic issues. For example, if we think to historical places. On the other hand, markerless methods solve the previous gaps, but for example, GNSS-based methods, even if they work very well for large outdoor environments, they cannot be applied indoor, for example. Structure from motion and image comparison methods solve SLAM and visual SLAM issues related respectively to drifts and closed loop, work very well indoor, but require a preliminary survey for collecting reference images of the environment. Hence, what we can say is that a unique solution applicable for both indoor and outdoor environment does not exist yet, and there is the need to define an AR registration system that works in unprepared environment. To this purpose, we identified at the first objective of this study the definition of a seamless markerless AR registration system that works seamlessly in both indoor and outdoor environment, and that is infrastructure-free. In addition, the study aims to quantify registration drifts during facility management operation in order to define the required spatial temporal registration frequency. And to address the first objective, we have integrated in a system architecture the most performing markerless technologies illustrated in this taxonomy that are computer vision and GNSS RTK ones. We integrated this one, as I said before, into a AR cloud platform described by this system architecture that is based on two registration engines that we will discuss in more details in a few seconds, a switch engine and a database. Starting from the first AR registration engine, that is the image-based AR registration one, we can say that it works in both indoor and outdoor environments. So we can say that we could have also used this approach for outdoor application, but it turns out to be not convenient to create and manage huge image datasets on a geographic scale. And for this reason, we integrated the image-based one with the GNSS RTK technology, since it is the best solution, as I said before, for large outdoor environment. Finally, the switch engine manages the switch between the two previous engines, ensuring a seamless indoor-outdoor registration. In this study, the proposed architecture was implemented considering Microsoft HoloLens 2 as the AR client. So now let's go into the details of the two engines. As you can see in this slide, there is a big pictures of the implemented system architecture. The GNSS RTK registration engine on the left in this slide relies on the combination of a GNSS RTK tracking system and the HoloLens 2 built-in inertial tracking system. Registering these two systems ensures a 6 degree of freedom localization of the AR device and therefore an accurate alignment of virtual objects to the real space. In the image-based registration engine, instead, that is depicted on the right in this slide, a 3D mapping must be carried out one-off using a LiDAR scanner or applying structure from motion technology to reference photos collected in the considered environment. Afterwards, query frames of the HoloLens 2 can be localized with reference to the 3D mapping using a combination of two technologies that are the hierarchical feature networks plus the perspective and point algorithm. The implementation of the overall system requires the settlement of a technology stack that included the installation of the RTK base station on the top of the highest building of our university. This base station has a 10 kilometers radius coverage, just to provide some numbers. The 3D printing of a Regi support that firmly connects the RTK receiver to the HoloLens 2 device. Then the generation of a 3D mapping using, in our case, GeoSLAM, that directly provide point clouds and registered images, and ColdMap that applies structure from motion to generate a sparse point cloud from photos collected in the environment. Then what we did is the generation of a database storing point clouds and registered images of the 3D mapping, and finally the development of a HoloLens 2 application in Unity 3D using the C# programming language available inside the gaming environment. We tested the developed prototype system in a real case study related to the facility management of the DC3 labs electrical system at UNIVPM campus, so our university. Here we assume the technician has to inspect both the indoor-outdoor environment, as you can see in this video, and specifically an electrical panel inside the lab, located in the red place mark in the left figure in the slide, and its cables, which can be inspected through the outdoor manhole about 100 meters from the building located in the blue place mark in the left figure. In this context, the developer system, as you can see in the demo video, can help to speed up the operation of locating the assets subject to facility management operation. In this study, we quantified the registration accuracy, and so we passed the second objective of the study, focusing only on the GNSS-based AR registration engine. So we carried out two experiments in the DC3 lab case study. The first one considered the simulation of facility management operation in a mixed environment and consisted in executing only web registration outdoor at the beginning of the path. Instead, in the second experiment, we focused only on the outdoor environment and we executed one registration each 20 seconds. The results of the first experiment are reported by this chart, as you can see. So here we have the point A in this chart, that is the point in which the registration was carried out at the beginning of the experiment. You can see also the path tracked by the HoloLens 2, represented by the blue dots, and the one of the GNSS RTK, represented instead by the orange dots. For these points, you can see also orange error bars to indicate the GNSS RTK localization accuracy, and according to this accuracy, three zones were identified. The first one is the area inside the laboratory. where the large error bar size confirmed that the GNSS RTK is inadequate for indoor application due to scarce signal, as you can imagine. The area close to the door, instead, is a typical urban canyon where the GNSS RTK exhibited reduced reliability due to scarce signal, as I said before. So what we can conclude from these two first results is that in both this area there is the need of a supplementary system, that is the image-based system that does not rely on a GNSS RTK signal. Finally, for the outdoor area, results are further detailed by this second chart. As I said before, in this experiment, the registration between the GNSS RTK and the HoloLens 2 tracking system was carried out only once outdoor at the beginning. So this chart depicts the drift of the HoloLens 2 tracking system from the GNSS RTK ones, corresponding to about 1 meter after 45 meters traveled by the user. This result confirmed the need to carry out regular registration of the tracking systems to contain drifts during facility management operation. So in order to define a spatial temporal registration frequency and correct this drift, what we did is a second experiment. This experiment was carried out outdoor. To this purpose, the outdoor path that you can see in the highlighted area was divided into 6 subsets of 20 seconds each. The registration in this path was carried out at the beginning of each subset, and the position tracked once per second. According to the literature, 10 centimeters is the fine precision positional accuracy threshold. That is the minimum accuracy required, as stated in the literature, for a good AR user experience. The red dashed line in this chart is the trend line of all subsets that shows that the drift remains below 10 centimeters within about 4 meters of covered distance by the user. Instead, the light green curve in this chart, reporting the worst performance of the subsets, show that the drift remains below 10 centimeters only within about 2 meters of covered distance and around 1.5 seconds of tracking. Hence, the results underscore the need of aligning the HoloLens 2 tracking system with the GNSS RTK once approximately every 1.5 seconds or 2 meters of traveled distance. And to conclude, we can say that a seamless markerless AR registration system integrating two technologies, GNSS RTK and image comparison, was developed and implemented to support facility management operation. It was tested in a real case study related to the facility management of a university campus, and experiment results related to the GNSS RTK engine showed that the drift between the GNSS RTK and HoloLens 2 tracking systems are about 1 meter after 45 meters traveled outdoor. This result confirmed the need of a periodic spatial registration of the proposed system, and the experiment also showed that a registration frequency of about 2 meters or 1.5 seconds is required to ensure a fine precision positional accuracy. As a future work, what we can say is that there is the need to test the accuracy of the indoor engine, to implement data fusion between the two registration engines, and assess the accuracy of the whole system. Thank you very much for your attention.